Welcome back to my kitchen. I don't know if you've ever done this, but if you have a sink and you turn on that sink, you can see this sort of weird ring where the water is like going really fast and is really shallow for a little while, but then it all of a sudden jumps up to a much thicker and slower moving thing. So it's like moving really, really fast, and then all of a sudden it jumps up and the water gets deeper, moves a little bit more slowly. So you can almost see there's this sort of ring around where the faucet hits, where there's this one region where it's really fast and really shallow, and this other region where it's slow and deep. This is an opportunity for us to do some fluid mechanics. Let's talk about the hydraulic jump. So let's talk about the hydraulic jump. So what do I mean by the hydraulic jump? It's this phenomenon where you have it's this phenomenon in fluid mechanics where you have, let's say, some flow. We're going to say gravity is in this direction, and there's two sort of distinct regions of the flow. One region of the flow where the flow comes in and it's moving pretty fast and the flow is pretty shallow, and then there's this sort of tumultuous, turbulent jump, and then the flow kind of sorts itself out afterwards and increases in depth. And the way we're going to analyze this is we're going to sort of, this is kind of a side view, right? So when we were looking in the sink, we kind of had a top view, but you can imagine, all right, I'm looking at the side of the sink right here. This is the basin of the sink, and I'm sort of looking at a side profile of the flow. So, you know, the faucet emptied somewhere over here. The fluid came in, let's say pretty fast with some velocity v1, and it had, let's say, a pretty narrow depth h1 in this region. And then let's say the flow exits in this region, and it has some much deeper depth, let's call it h2, and it has some different velocity. And spoiler alert, this velocity is going to be a smaller velocity than v1. We'll call it v2, and it's as of yet unknown. So we're going to give ourselves the challenge. You up for a challenge? I'm up for a challenge. Let's give ourselves the challenge of, hey, if we knew the input velocity and the input depth of the fluid, could we predict both the output depth and the output velocity? So we're going to use the crystal ball of fluid mechanics to make this prediction. So we want to predict these based on these known inputs. So our known inputs are going to be in blue, our unknowns are going to be in red. We want to predict these outputs based on this. And if you imagine, if I have two unknowns, I'm going to need at least two equations in order to solve for these unknowns. So we got a challenge ahead of us. Let's go ahead and do it. So what's going to be our problem-solving strategy? So what's our plan? Well, because we have two unknowns, we're going to need a couple of inputs or a couple of equations to help resolve those unknowns. So we're going to need to think about a couple of equations. And anytime I think about, you know, flows in and flows out, I might think of, hey, I'm going to need to apply conservation of mass, because if you have some system and some flow in and some flow out, you can in general get some kind of relationship between input flow and output flow. And it turns out that although I'm not explicitly talking about what forces might exist on this control volume, we're also going to need to apply conservation of momentum, because oftentimes, if we just applied conservation of mass, that would give us one equation, but we have two unknowns that we're looking for. So anytime you're looking for two things, you might need to rope in a second equation to deal with that. And if we're applying conservation of momentum, when we apply conservation of momentum, we need to choose which momentum we're conserving, right? Momentum is secretly a 3 for 1. It could be x, it could be y, it could be z momentum that we could apply to this equation. And it turns out, or apply it to this system, and it turns out that, well, let me define my coordinate system right here. Let's put x in this direction and z in this direction right here. It turns out that, in general, if you're thinking about conservation of momentum, usually it's best to apply conservation of momentum in the directions where we have some kind of velocity change, right? So I have some velocity going in, and it's an x velocity, and also as I go out, the x velocity has changed. So anytime you have a change, some velocity that changes in some direction, it's probably going to be conservation of momentum in that direction is probably going to be the useful one. So in this case, it's going to be conservation of x momentum. And then when we're applying conservation of momentum, it turns out that one of the forces on this control volume is going to be due to pressure. So we're actually going to need to rope in hydrostatics. And I'm going to put statics in quotes because, strictly speaking, this water is moving, but well, let's cross that bridge when we get there. So we're going to need to actually rope in a lot of the concepts that we've talked about so far in class. We're going to talk about conservation of mass, conservation of momentum. We're going to apply both of these, and when we're resolving some of the forces involved in conservation of momentum, we're going to pull in some information or some problem-solving strategies and some concepts from hydrostatics as well. And ultimately what we're looking for is two equations that have H2 and V2 in them, so we can do two equations, two unknowns, and get to some result. As we're moving along, so this is our plan. As we're moving along, let's build a list of assumptions. Let's build a list of assumptions as we're going along in a sort of sidebar right here. And spoiler alert, we're gonna need to make a whole bunch of them. So let's go ahead and do that. So let's start with applying conservation of mass. But secretly, before we do conservation of mass, and conservation of momentum, I need to actually, before I do either of those, I need to define my control volume. Because we know that conservation of mass and conservation of momentum both must apply. We can only really apply those to a control volume. And when we think about control volumes, we need to think sort of sensibly about these control volumes in order to get results that are kind of useful. So what can we do? So when I think about control volumes, one strategy for defining control volumes is to make the boundaries of our control volumes perpendicular to flows. So here I have a flow, the flow is kind of going like this, V2, so I'm going to make one of the walls of my control volume perpendicular to this part of the flow. And I'm going to make another part of my control volume, this part, perpendicular to this input here. Another strategy for control volumes is to make the surface of the control volume parallel to parts of the flow. So another surface of my control volume, I'm going to make parallel with the surface here. And if I sort of by definition make this part of the control volume parallel with the surface, then all the fluid along this part of the control volume is essentially going along the control volume. Nothing is crossing into it or out of it if sort of by definition it's coincident with this surface here. So I'm going to have an inlet surface, an outlet surface, one surface that's kind of coincident with the top surface of the fluid, and then I'm going to make another one, and I'm going to be a little sneaky here. I'm going to imagine that there's a boundary layer where, strictly speaking, we know that the fluid has to have zero velocity right next to the wall, but I'm going to imagine that there's some thin boundary layer where the flow transitions from being zero right at the wall to whatever V2 is over here, or whatever V1 is over here. So we're going to assume that there's a thin boundary layer. Again, the details of how well we can justify this thin boundary layer assumption are sort of beyond the scope of what we're talking about in class right now, but again, I'm hand waving, take my word for it. Let's make a surface kind of coincident with this boundary layer. So we don't need to deal with kind of any of the messiness of what's going on between this sort of more uniform region of the flow and the details of what's happening at the wall right here. So let's make this thin boundary layer assumption. All right, let's number our surfaces. Let's make surface number 1 our inlet. We'll make surface number 2 our outlet. I'll make surface number 3 this top surface here, and I'll make surface number 4 this part of the thing that's basically just barely outside of this boundary layer, but very close to the bottom of the flow. So if I do conservation of mass, well, let me put down my conservation of mass equation here. ddt of the quantity and integral over the volume of our control volume of rho dv is going to be equal to minus the integral over the surface of rho times the quantity v dot n dA, and there's no generation term, so that's basically plus 0. So there we have it. Now, I'm going to try to square away the left-hand side of the equation as possible. So if you either rewind to or zoom back to the part of the video where we were looking at that flow, there was a little bit of kind of turbulence, unsteadiness right at this interface here, but fundamentally, when I had that faucet going, this flow here was kind of constant, right? There was sort of one single velocity and one single depth, and if I took a snapshot at the beginning of the video and towards the end of the video, as long as I wasn't moving the whole faucet around, talking or putting my fingers in there, this was pretty constant with time. And as well, this downstream surface was pretty constant with time too. So we're basically going to assume that we have this hydraulic jump system in steady state. And if we have a steady state, the derivative of basically anything with respect to time is going to be 0. So I'm going to save myself the trouble of having to deal with this integral of rho dv by just saying, hey, I'm analyzing this system only in steady state, which basically means that the time derivative of anything is going to be 0. So our steady assumption helps us do this. Who likes getting rid of messy integrals and derivatives and replacing them with 0? I do. All right, now we're going to take the right-hand side of this equation and we're going to break it up into the 4 surfaces. So let's go ahead and do that. So we have an integral over surface 1. We're going to assume that we have some uniform density fluid in our coming out of the sink, right? It's not like honey comes out of my sink and then later on it gets replaced with water or something like that. Although, I mean, that would be a pretty interesting sink. So basically we're just going to treat some uniform density of the fluid up here. We're going to treat that as a known constant. So we have rho times v dot n dA, and then over surface 2 we have rho v dot n dA, and we can do it for the rest of them as well. All right, now, can we make any simplifications to any of these integrals here? Well, let's do it. Let's look at surface 1 first. That's this surface on the left-hand side here. If I think about what direction n is pointing, remember n is my outward pointing normal. So in this case, n is pointing to the left, and the velocity at this surface is pointing to the right. So v and n are in opposite directions. So v dot n is going to have a magnitude of v1, but because they're in opposite directions, I'm going to get a minus sign. So 0 equals minus the integral over surface 1. We still have rho. And in this case, v dot n is going to be minus v1. And we're going to have dA. We're going to have surface 2, and over surface 2, I have rho still, and in this case, v n points to the right because it's my outward pointing normal on surface 2, and v2 points to the right as well, so their dot product is going to have a magnitude v2 and it's going to be positive. dA. All right, now I have my integral over surface 3. If I think about my surface 3, the velocity at any point on surface 3 is going to be sort of pointing along the surface, right? We defined this part of the control surface to sort of be coincident. So velocity must be going along the surface. If velocity were going against the surface, then the surface would be bulging out. But n is pointing like this. If these two things are perpendicular, then their dot product is going to be 0. So we basically get 0 in this third term. And we can follow a similar argument for this bottom term right here. You know, velocity is basically going along the surface. We don't really have anything crossing the surface, because if we did have something crossing the surface, you know, where would it go? It would go in the ground? No, that's not happening, right? So, so we can follow a similar argument for surface 4. Surface 4 as well. So what does this mean? These basically go away. These basically go away. And we have these left. All right, progress. So, so I haven't talked about sort of what's happening in the, I guess, if this is x and this is z, what's happening in the y direction, you know, what's happening out of the page. So we're just sort of imagining that this system is kind of a, I'm going to attempt to draw 3D here, but we're sort of imagining that this system is kind of exists in 3D. And, you know, H2 is this depth here, H1 is this depth here, and, you know, without really loss of generality, we're sort of assuming that the same thing is happening no matter what position we are into or out of the page. We're sort of imagining it's the same thing happening, you know, all the way into or out of the page in this direction here. So I'm just going to basically say, hey, let's just imagine that this system has some, you know, some width into the page, and I guess let's just call it, I don't know, let's just call it B. Let's just say that there's some width to this whole system in this direction, B. So there we have it. All right, so how does this help? How does this little side thought help our analysis here? Well, if we bring this equation down, we now have 0 equals, well, can we pull some stuff out of the integral? Heck yes, as long as we make some assumptions. So let's assume v1 and v2 are uniform. And again, as long as we're sort of out of this boundary layer, that's not a bad assumption. It's not too bad. So we're going to assume v1 and v2 are uniform. And we already assumed rho is uniform. So what does that mean? We can basically pull these things out of the integral. Again, if they're uniform, they're not varying spatially across their respective surfaces. So both of those could pull out of the integral. So what does that leave us with? We have 0 equals, well, we have minus and negative here. We have 0 equals rho v1 times an integral dA of surface 1, and then we have minus rho v2 of an integral surface 2 dA. Oh, sorry, v2 is an unknown. Ah, it's not blue, it's red. Red. So there we have it. V2 is something that's as of yet unknown. All right, so where does that leave us? Well, what are these integrals? Well, anytime you integrate dA, you just get a, right? Anytime you integrate dx, you get x. Anytime you integrate d whatever, you get whatever. So if we have integral dA for surface 1, this is just going to give us the area of surface 1. Well, what's the area of surface 1? Well, it's the height, it's this surface 1 is this one right here of our control volume. And what's the height, what's the area of this rectangle? Well, it has a height h1 and a width b. So this integral dA is essentially the area of this surface right here. The area of the surface right here is this height times its width. So what's that going to look like? We're gonna have 0 equals rho v1 times b times h1. And we can follow a similar argument for this downstream surface. Integral dA over surface 2 is just the area of this second surface right here. It's the area of that second surface, which would be b times h2. So this is going to be b times h2, and of course we have our rho v2 as well. So what does that leave us with? We have rho. We still have our v2, and then the integral, we get a b and an h2. All right, awesome. So what does this leave us with? Well, if you notice, both terms have a rho, so we could divide that. Both terms have a b, so we could divide that. We could bring this over to one side of the equation, and what are we left with? We're left with v1 h1 is equal to v2 h2. So what does this mean? Basically, if we apply this idea at the inlet, in the inlet we had fluid that was very fast, i.e. a large v1, but h1 was pretty small. So their product ends up being the same as the product of v2 and h2 over at the other side. Well, where at the outlet the fluid was moving a lot slower, so we had a small v2, but the depth was much deeper, h2 was bigger, and these ended up canceling. It ended up so their products, the product of v1 h1 is the same as the product of v1 h2, and in a sense this is sort of this is a result of conservation of mass. It's basically saying the same amount of fluid is flowing in as flowing out. So what do we have here? We have one equation. This equation comes out from conservation of mass, but we have one equation. We have some in terms of knowns, but we have two unknowns. So we're going to need another equation to resolve these unknowns, and hopefully this equation involves v2, h2, or both of them, such that we'll have two equations and two unknowns to determine them. So what's the next step? Well, we're going to need another equation to resolve this, and as I talked about earlier, we're going to need to apply conservation of momentum, and in particular x momentum, to help get another relationship between v's and h's and all that stuff. So let's go ahead and do that. So the full form of conservation of momentum is d dt of an integral over the control volume of velocity vector rho dv, and that left-hand side is equal to negative an integral over the surface of velocity vector rho v dot n dA plus the sum of any external forces applied to our control volume. And we're interested in just the x component of this. So remember that when you're dealing with conservation of momentum and you're taking with the x and you're taking just one component of this conservation of momentum equation, you leave these alone. So these stay as dot products of vectors. And these are the three, and these things are the things you take x components of, or whatever component you're interested in, but in our case we're going to take x. We're going to take the x component of these things. So what does that look like? Well, we have d dt of an integral over the volume of our control volume of vx rho dv is equal to minus an integral over the surface of Vx times rho times v dot n dA plus the sum of any x external forces on our control volume. So there we have it. Now, so this is the x component. This is the full conservation of momentum, which is, because it's a vector equation, is secretly 3 equations in one, x, y, and z, equating all of those components to each of their respective components. And here we have just the x, the equation relating the x components of momentum. And this is going to be the one that's useful to us to sort of get another relationship between velocities and heights and all that stuff. So we have this. Now, we have this equation. Can we make any simplifications to it right off? Well, if you remember, back when we did conservation of mass, we were able to say, hey, we have, our system is in steady state here. So we were able to just right away say, hey, whatever this integral is going to be constant. And it turns out, whatever integral this is also going to be constant. So, we don't really even need to bother calculating what it is. We know that it's a constant because our system is in steady state. So the time derivative of a constant is going to be 0. So we can go ahead and we can get rid of this term, and it's basically 0 because we're in steady state, i.e. the natures of the flow in and the flow out aren't varying with time. So what does that leave us with? We've already defined our control surface, right? So in the same way that we had some integral over the surface for conservation of mass, and we broke it up into 1, 2, 3, and 4, right here, we're going to break up this surface integral also into 4 parts. So what is that going to look like? We're going to have minus an integral over surface 1 of whatever Vx is, on surface 1. Well, Vx is V1 on surface 1. So Vx for surface 1 is V1. And then we have rho at surface 1. And then we have V dot n for surface 1. And V dot n for surface 1, well, we already figured it out. V dot n is minus V1. So just to clarify here, Vx for surface 1, right? Vx is positive V1 because it's just basically like, hey, what is the x velocity of the stuff here? Whereas V dot n for surface 1 is minus V1 because V1 goes in this direction and n goes in the other direction. So Vx is positive V1 because V1 is going in the positive x direction. V dot n is minus V1 because V1 and n are going in opposite directions. So that's why these two terms are different from one another. And then we have our dA right here. Then we have minus an integral over surface 2. And on surface 2, Vx is going to be V2. And that's positive V2, right? Because V2 is also going in the positive x direction. We're going to have a rho. And then we're going to have V dot n for surface 2. And V dot n for surface 2 is going to be positive V2 as well. And then we're still going to have our dA. So take a moment now and see if you can work out what this term is for surface 3. So pause and ponder. Pause and ponder what the integral is going to be for surface 3. Well, how does it work out? Vx, we don't really need to worry about what Vx is. I mean, I'm just going to leave it there. Rho is going to be rho. But in the same way that for surface 3, V dot n was 0, it was V dot n was 0 for the conservation of mass integral, basically because the velocities go just along the surface, and n and v are at right angles to one another. V dot n is also going to be 0 for the conservation of momentum integral, right? It's the same V dot n, so it's still going to be 0. All right, and we have dA, so that basically means this whole term is gone. And we could make the same argument for surface 4. There's some V dot x along surface 4. Who knows what it is? I don't care, because I know that the v dot n for surface 4 is also going to be 0 dA. So this term goes away, and then we still have our plus sum of x external forces. So, so there we have it. So take a moment now, pause and ponder, perhaps. Pause and ponder. What simplifications can you make to these two integrals here? All right, so we're going to have 0 equals. What can you do to these two integrals to perhaps follow a process similar to what we did here? What can you do here to make some progress? To get these integrals, not in terms of funky integrals dA, but in terms of stuff, known constants that we care about. So hopefully you had a chance to think about it. Let's work it out together so we can make sure we all got to the same page. So all of this stuff, all of these, under the same assumptions that we already made earlier, can come out of the integral, right? V1 is constant if it's uniform across V1. Rho, we said, was a constant. Same arguments for V2s. So then when we pull all of that out of the integral, we get V1 squared rho. And then we're left with integral over surface 1 dA, and the minus is canceled out. Then we have minus V2 squared rho integral over surface 2 dA, and then we still have our x external forces. These two are of course 0. And then if you remember, we basically already came up with rationale here, right? These integrals dAs just become areas, A1 and A2, area of those two surfaces respectively, and we already went through this reasoning here to say that the first surface was h1 times b, and the second surface was h2 times b. So we can go ahead and plug those in. So 0 is equal to v1 squared rho b h1. And then we have minus v2 squared rho bh2. Now, and then we still have our sum of x external forces. So now let's start squaring away these external forces. And I'm going to sort of draw the control volume, and we can consider what forces might be acting on it. So first I'll draw the control volume, and then we'll try to carefully consider what forces might be acting on it. So I'm going to draw a little side view right here. And we have basically a chunk of fluid that looks like this. We know gravity's pointing downwards, and we have a coordinate system. We said z was like this, and x was like this. So, so here we have it. Let's kind of carefully consider our forces. And you remember, if you dust off your notes from when we were talking about conservation of momentum, these external forces can basically come in 4 flavors. So let's square them out. So the sum of forces in x external basically come from 4 things. We can basically say there's some force of shear stress, perhaps in x. There's some force of pressure in x. There's some force of gravity in x. And there's also potentially some force through solids in x. So take a moment now, pause and ponder. which, if any of these forces, can we just get rid of right away? That, sort of by inspection, we know are zero. So take a moment, pause and ponder. Can we get rid of any of these forces? All right, well, hopefully we've had a chance to pause and ponder. Through solids, let's think about through solids. If we think about our control volume, do any parts of the surface of our control volume cut through a solid? Well, no, they're all, this control volume is entirely within the fluid. So if your control volume, if all the surfaces of your control volume are entirely within the fluid, there can't be any forces through solids, right? So our CV is all fluid. Can we get rid of any other ones? Yeah, we can get rid of gravity, right? Gravity's in the z direction here. So is there any x component of gravity? G in z, not x. Force of shear stress and pressure. All right. Well, spoiler alert, pressure is going to be present, and shear stress is actually not going to be present. So I'm going to just tell you that it's zero and then explain why. So let's think about what surfaces there could be shear stress on. Well, if I think about these two surfaces here and here, even if there were shear stress on these surfaces, it would be in the z direction, not in the x direction. So there's no shear stress on surfaces 1 or 2. If I think about surface 3, if we're analyzing liquids, pretty much in general, any interface that's between the liquid and the air has negligible shear stress, almost no shear stress. Basically, air has such low viscosity and density and all that the air virtually can't apply any shear stress forces to the fluid. So surface 3 has no shear stress as well. And surface 4, well, strictly speaking, yeah, I mean, there might be some shear stress, but if we analyze ourselves outside of the boundary layer, if we're analyzing our control volume just barely outside the boundary layer, if we're barely outside the boundary layer, then we're in these regions where we have pretty much uniform flow. And if we have uniform flow, then velocity isn't varying in this direction anymore. And if velocity is not varying in this direction, then there's no velocity gradient. If there's no velocity gradient, there's no shear stress. So we're basically going to say we're outside the boundary layer, which basically means that velocities are uniform. And if velocities are uniform, there's no dvx, I guess dz. And if there's no velocity gradient, then there's no tau. And then this is basically for surface 4. And we already made arguments for surfaces 1, 2, and 3. So if we analyze all of these surfaces here, we know actually, in the strictest sense, yeah, there's probably a little bit of shear stress, but that shear stress is, spoiler alert, going to be, negligible. For simplicity, and it's a reasonably good assumption. So all of the x external forces, the only candidate left here is pressure. So let's think, pause and ponder, again, if you reach this conclusion, will we have forces in the x direction due to pressure? So repause and reponder. Well, hopefully you've had a chance to pause and ponder this. It turns out, yeah, we're going to need to deal with pressure from these forces in x. And if we, strictly speaking, these fluids are moving, so we really can't quite assume hydrostatics. But for lack of a more sophisticated model, a more rigorous model, let's assume pressure to a first approximation is approximately hydrostatic. Approximately, that pressure is basically on these two surfaces from the fluid. You know, even though strictly speaking the fluid's moving, let's say give or take a little bit, it's hydrostatic. So what is that going to look like? Well, if you think about it, we're going to have pressure. Pressure's going to be acting inwards on these surfaces. Pressure's going to be, let's work in gauge pressures. Pressure's going to be 0 at the top, and pressure's going to sort of increase linearly with depth on this side, right? So we have pressure. Pressure pushing inward on this face, and we also have pressure pushing inward on this face. So in a sense, pressure on this face pushes the control volume this way, pressure on this face pushes the control volume this way, and if we're thinking about it, hey, these two pressures aren't going to balance each other out, because this pressure is going to be lower in magnitude because it's in general kind of shallower from the surface point right here. That's at, you know, 0 gauge pressure, compared to this one. So we achieve a lot higher pressures on this right surface, and there's more area, right? So these two pressures, they're not gonna balance. So they won't be equal. And if they're not equal, then there's gonna be some net pressure force. So let's try to figure out what this net pressure force is. So let's break this pressure force, this net sort of total pressure force, into two pieces. So we're going to break it into one force for surface 1 and another for surface 2 here. So we're basically going to say it's whatever pressure force would be from surface 1. And oops, I made a little mistake here. If we think about it, the pressure on surface 1 is going to be pushing us in the positive x direction, whereas the pressure on surface 2 is going to be pushing us in the negative x direction. So pressure on surface 1 contributes positively to our net x force due to pressure, whereas pressure on surface 2 contributes negatively. So that's why we have this minus sign right here. And if we think about pressure, we can think back to the example problem where I was trying to hold up the wall of the tub. And it's almost the same problem here, where we can kind of analyze surface 2 as a wall of the tub. We can analyze surface 1 as a wall of the tub, you know, and basically pressure's acting on these surfaces. And if you recall for this problem, you know, when pressure's non-uniform, what do we need to do? Well, if pressure's non-uniform, we need to slice up these surfaces and then integrate pressure to get some net force, right? So if pressure's uniform, then you can just do force equals pressure times area, but these pressure distributions are non-uniform, so we need to slice it up and then integrate to get the net force. So what's this going to look like? We're basically going to need to integrate over surface 1, whatever the pressure is on surface 1 times a dA for surface 1, and then we're going to need to integrate over surface 2, whatever pressure exists on surface 2 times dA. And these will give us these integrals of pressure times dA. We're essentially taking these surfaces and slicing them up into a bunch of little chunks because pressures are non-uniform, so we need to get net forces by integrating those pressures. So how do we slice out the surface? So take a moment, pause and ponder, perhaps go back to your notes where we did the bathtub problem and see, you know, what's a sensible way to slice up this? What's a sensible way to define our dAs for this surface? Well, a sensible way to define your dA, if you remember, if we have a dA, we want to break up our dA into sort of a multiplication of two things. One is we're going to keep a d something, and the d something is the dimension along which whatever else in your integral is going to vary. So pressure, we anticipate pressure being a function of z, right? Pressure varies with depth. So part of our dA is going to be dz. And so part of our dA is going to be dz. And what does dz look like on our control surface? Well, if you break up this we'd have a dz right here, and we're basically taking our surface and putting it into a bunch of narrow slices. And basically, if we make our dz arbitrarily small, for each slice, pressure's a constant, and the area of that slice is the width of our control volume, B times dz right here. So dA is simply B times dz. And we can do basically this, and we can do virtually the same strategy for surface 1 versus surface 2, right? So dA for either surface 1 or surface 2 is going to be B dz. All right. We still have a little bit of work to do on this integral. We anticipate integrating with respect to z, and we anticipate pressure varying with z. So now our goal is to get pressure as a function of z, and because these pressure distributions are different from one another, we're going to need two different functions. We're going to need one for essentially pressure on surface 2, right? We're going to need one function to describe this pressure distribution and another to describe this, because obviously these two pressure distributions are very different from one another. So we're basically going to need two different functions to describe pressure. One for surface 1 and one for surface 2. So in this case, we want pressure on surface 2 as a function of z. All right, so let's go ahead and do that. See where that gets us. All right, so let's look at pressure 1. Let's look at surface 1 here. So pressure on surface 1, and so if we assume constant density and constant g, which we've basically already assumed, we can use the already integrated form of that hydrostatics equation, which basically relates pressure at some point. I'm just going to say there's some point right here between the floor and the surface of, we get to the surface, and I'm going to relate that to this point at the top right here. So pressure here minus pressure at the top, which is 0, because we're dealing with gauge pressure 0, is equal to minus rho g z, because we're basically saying pressure at some arbitrary point z, so P corresponds to z, and then whatever z level corresponds to this pressure, minus whatever z level corresponds to this pressure, I'm using this as sort of my reference point for pressure. And the z at this point right here is H1. So this equation right here describes this pressure distribution right here. Similarly, we'll need another pressure distribution for this one, so I encourage you to pause and ponder. Try to get the pressure distribution for this side. So take a moment, pause and ponder, see if you can get that. All right, well, if we choose some arbitrary point right here, we get pressure here, and we choose our reference point right here, basically pressure equals 0 here, and z is equal to H2 right there. We end up with this pressure distribution right here. So what can we do now? We can take this pressure distribution and we can plug that in here, and we can take this pressure distribution and plug that in here, and because both of these are basically functions of z, we'll be able to compute these integrals in a pretty straightforward way to get our net pressure x force. And it turns out that, from our thoughtful analysis here, this net pressure x force is actually all of the external x force. And then once we do that, we can plug it into here, into our conservation of momentum. Ooh, man, we're getting like equations upon equations deep here. But then hopefully we'll have some relationship between velocities and heights and all this other stuff that we care about. So let's go ahead and try to plug these in and do these integrals. So an integral over surface 1 of minus Now, before we go ahead and churn out these integrals, let's think about what these limits of integration should be. So take a moment, pause and ponder. What should the limits of integration be on this integral, and what should the limits of integration be on this integral? So pause and ponder. What should those limits of integration be on all of these integrals? So hopefully we've had a chance to pause and ponder. The limits of integration are basically correspond to the lower and upper limit that we're integrating pressure across in here. So we basically define z equals 0 to be the bottom here. So we're integrating from z equals 0 and then to z equals h1 on the first surface. And then for the second surface, we're integrating from z equals 0 all the way up to h2. All right, so now take a moment, pause and ponder, and try to work out these integrals for yourself. It's always good to get some practice doing integration. So a lot of this stuff can come out of the integral. Hopefully you had a chance to pause and ponder. A lot of this stuff can come out of the integral. So what do we get? Get plus because these two minuses cancel out. We get rho g b. When we integrate z, we get 1/2 z squared. And then when we integrate h2, h2 is of course a constant with respect to z. We get h2z. And of course these would be evaluated from 0 to h2. When we evaluate these at the limits of integration, the zeros obviously, we don't need to, the zero is just plugging in, we get 0 for everything for the lower limits of integration, so we can essentially just plug in the upper limits of integration here. And what does that give us? Getting on the home stretch here, we get minus rho g b 1/2 h1 squared minus h1 squared, right? When we plug in h1 here, we get h1 squared. And then we have plus rho g b 1/2 h2 squared minus h2 squared. These, we can work on these a little bit. And and we basically get this 1/2 h1 squared minus h1 squared, and the minus out front, we end up with rho g b 1/2 h1 squared minus rho g b h2 1/2 h2 squared. I guess 1/2 is a known constant, but you get my drift, right? So this is our F net pressure force in X, which from our earlier conclusions right here, we basically said is equal to the sum of external X forces. We can now take this and we can plug it into this result, this F external forces that we got from conservation of X momentum, right? We can plug that in here, and then we'll have an equation entirely in terms of known constants, V2s and H2s. Awesome. So let's go ahead and do that. All right. So this equation here is conservation of X momentum for this particular system. So we basically have this equation, conservation of momentum, and I'm just going to take conservation of mass and sort of put it down here just so we have it at the ready. We now have conservation of mass, which basically is V1 H1 equals V2 H2. So what do we have at our disposal? Right, this is conservation of mass. Conservation of mass gave us this equation. So now we have two equations and two unknowns. It's a little bit tricky. It's not two linear equations, right? We have some squareds and all that other business. So this there's not a trivial amount of algebra to solve this, but let's give it our shot. So let's go ahead and try to solve this system of two equations. All right, so first what I'm going to do is I'm going to solve conservation of mass for one of these variables and then plug that into this other one such that I'll have a somewhat messy but one equation with only one unknown at this point. So I'm going to solve this easy equation for one of the unknowns and then plug it into the other one. So let's go ahead and do that. One thing that, yeah, so we have this equation right here. So if I solve this equation for V2, I can basically say V2 is equal to V1 times H1 over H2. Right, I essentially take this equation and divide it by H2. I can get this result right here. Then I can take this equation right here and I can plug it into conservation of momentum right there. So if I take this and plug it in for conservation of momentum right there, what do I get? Well, actually, before I go ahead and plug this in, if we notice, all of these terms in conservation of momentum have a rho. That I can get rid of. So first things first, I can just get rid of all the rows in conservation of momentum. If we also notice, all of the terms in conservation of momentum have a b as well. So oops, sorry. So we have a little sidetrack here. So I took conservation of mass, solved it for V2. I also canceled out all the row B's from all the terms in here, essentially dividing everything by row B. So what is that going to give us? Once we plug that in, we'll end up with 0 equals this first term here. So it's going to be V1 squared H1. And then we're going to have minus, and when we plug in this here, we get V1 squared, right? Because we're squaring this term here when we plug it in. We get V1 squared H1 squared over H2 squared. And then we still have an H2 right here. Then we have plus G times 1/2 H1 squared. And then we have minus G times 1/2 H2 squared. All right, so let's see where this gets us. All right, so let's take this equation, and I'm just going to pull a little trick. It would always annoy me when professors were like, oh, I already know the answer, so I'm just going to, tell you the trick to solving this equation. And I'm like, all right, great. How did you find out about that trick? But bear with me. I'm just going to tell us a trick. Let's multiply everything by H2. So we end up with 0 equals V1 squared H1 H2 minus V1 squared H1 H1 squared, right? Because we'd have an H2 in the denominator here. If we multiplied this term by H2, we'd then have an H2 squared, and that would cancel out. Then we'd have plus G over 2 H1 squared H2. Again, we're multiplying everything by H2. And then we'd have a minus G over 2 H2 cubed. And, if you're like me, you might look at this and be like, oh, yikes, how do I even solve this equation? So let me give you a little pro tip. You can plug this into Wolfram alpha. That's one strategy. It's a pretty good strategy, right? For all of your take-home quizzes, for all your homeworks, and to be honest, in real life, you're hardly ever going to run across an engineering scenario where you don't have Wolfram alpha at your disposal. Unless we sort of like run into the apocalypse where the internet is no longer available, in which case I think our concerns would be greater than what's going on here. You're always going to have Wolfram alpha at your disposal, right? So you could take this in and you could basically say, hey, solve this for H2. And if you attempted to solve it, well, we notice that this term is actually, this equation is actually essentially a cubic. We have an H2 cubed. We don't have any H2 squareds, but we have some H2s and then a constant term. This is actually cubic, and Wolfram alpha can solve cubics, and it can give you an algebraic result. So, strategy 1 is Wolfram alpha, and you could go ahead and do that. I want to, maybe I'm a masochist or whatever, but you could do things the hard way. I want to show you the hard way. Let's do things the algebra way. So no Wolfram alpha for us, although, I would recommend that you in real life actually go ahead and use Wolfram alpha to solve this. But, if you're curious, you can just bear with me for another minute or so and we'll solve this by hand. So let's do a little bit of algebra to manipulate this equation. So if you notice, we have some terms, right? We have like a G over 2 in these terms. We have like a V1 squared. So we can kind of do some, oh, sorry, I think I forgot an H1, right? If we can group some like terms, we can do some factoring, we can do some manipulations here. And if you end up, if you do a little bit of that and kind of bring some stuff over to one side of the equation to the other, you end up with V1 squared H1 times H1 minus H2 on the left-hand side is equal to, on the right-hand side, you end up with G over 2 times H2 times this quantity H1 squared minus H2 squared. And how do you get to this result? You basically get, you look at the right-hand side, you factor out a G over 2 H2 from the right-hand side. You look at the left-hand side, you sort of bring things over to the other side and factor out a V1 squared H, and you get this result. And if we're looking for 3 solutions, right? If we have a cubic, there are basically 3 roots. It turns out one of the roots, if you group things this way, one of the roots actually jumps out at you right away. One root is H1 equals H2. So let's just sort of say, hey, let's just sort of look at this result here. If H1 equals H2, the left-hand side becomes 0. If H1 equals H2, then we get essentially, these two terms cancel out and the right-hand side is 0. So what does this mean, H1 equals H2? Well, that basically means that the hydraulic jump that I described about here didn't happen at all. We had some fluid going in and the fluid just came straight out the other side unaffected. So I guess this makes physical sense to some extent. There are certainly points in the flow where the hydraulic jump didn't happen. So it makes sense that one possible outcome of this situation is that the hydraulic jump basically didn't happen. But, is that the interesting result that we're looking for? Nah, not really. So how do we get to our potentially interesting roots, right? So this is one of the roots of this cubic, and it's basically the boring hydraulic jump didn't happen. I mean, it's a physical result. It could the hydraulic jump could have possibly not happened, and momentum and mass would be conserved. Momentum and mass are conserved if a hydraulic jump doesn't happen. But we want to look for the case where the hydraulic jump did happen and momentum and mass are conserved. So we can take this result and divide by H1 minus H2. So we can divide both sides of this equation by H1 over H2. And if you do so, you end up with the following equation. And I'm going to skip a little bit of algebra here, so if you're curious, you can go back and check me on it. But we end up with V1 squared is equal to G over 2 H2 times H1 plus H2. And if I let myself kind of distribute the H2 over these two terms, I would notice that I get a quadratic. And quadratics, we could plug this into the quadratic formula to solve for H2. So if you're curious, you could go ahead and do that. And if you solved this quadratic, if you plugged into the quadratic formula and cared about your result, you would get H2. And actually, rather than solving for H2, I'm just going to solve for the ratio of H2 over H1. So you get H2 over H1 is equal to minus 1 plus or minus the square root of 1 minus 4. Or sorry. Scratch this out. I have a simpler version that I can just plop right on the screen here. H2 over H1 is equal to negative 1/2 plus or minus the square root, plus or minus 1/2 the square root of 1 plus 8 v1 squared over gh1. All right, now take a moment, pause and ponder. When you've solved the quadratic equation a million times, you end up with the plus or minus when you solve the quadratic equation. Which one should it be? Should it be plus or minus? So pause and ponder, consider. Should we take the positive root or the minus root in the plus or minus from this result? So what is the answer? The answer is you want to take the positive root. Why do we want to take the positive root? Well, if you took the minus root, then we would have a negative thing here and a negative thing here, and that would imply that somehow h2 is negative. So physically, what would that mean? That would mean that instead of having a hydraulic jump, somehow the surface of the water takes a nosedive through the floor to some negative z level. That makes no sense, right? So we get a non-physical root when we try to have that negative thing, implying that somehow h2 is negative, right? If we have a minus 1/2 and then a minus some chunk here that's positive. So we get this positive root right there. So what's our key result? Our key result is that h2 must be equal to h1 times minus 1/2 plus 1/2 square root of 1 plus 8 v1 squared over gh1, close parenthesis. Cool. All right, so there's our result. We can celebrate. We now have h2 entirely in terms of knowns. And if you wanted to go back and figure out, what v2 was, you could just plug this result back into your conservation of mass, right? You could just plug this back. You could just plug h2 back into conservation of mass. Right? We could just plug h2 in here and get v2 if we wanted to, right? We just plug this result back here. But I'm not even going to bother to do that because, whatever, who cares? I'm satisfied with figuring out h2. So what are a couple of sanity checks that we want to do? Well, I think the most important sanity check is units. Remember, baby you-know-who, she gets really upset when the units on both sides of the equation don't line up. So let's check units. h2 should have units of meters. h1 should have units of meters, and we're multiplying this by something that has no units. This has no units. And then v1 squared, well, we have the square root of v1 squared, which should have meters squared over seconds squared, over g, which should be meters per second squared, h1, which is meters. So conveniently, all of the stuff in the parentheses here, all the units cancel out, and that's good because we're adding it to something that is unitless, and we're adding this whole thing to something that's unitless, and that means this whole thing is unitless, and we just have meters on both sides of the equation. So units cancel out. So there we have it. Awesome. So that's our unit check. So hopefully this is a satisfying result. We basically had some system where we had two unknowns that we wanted to solve for, and we used both conservation of mass and conservation of momentum to get a predicted result for some height. So thanks again. Thanks for watching, and good luck with your fluid studies. Take care.